Hi everyone, and welcome back to my Basics of Flight Mechanics class. So today we're going to be covering the second part leading to the 3 degrees of freedom EOMs, and there are two things I want to talk about today, and that is the inertial velocity and the sum of the forces that will later make up the equations of motion. So the idea here is we want to be able to track the motion of the aircraft in the vertical plane, and that is going to be defined by the velocity vector. In order to derive an expression for the inertial velocity, we're going to need to exploit the inertial position, as we know that the derivative of the inertial position is going to be equal to the inertial velocity. The issue here is that the velocity vector is initially defined in the wind frame, whereas the position vector is defined in the ground frame. So somewhere along the line, we're going to need to transform these vectors from their original frame to a common frame, which in this case is going to be the local horizon frame. So in order to do that, we're going to use the properties of unit vectors, and that is that they have a magnitude and a direction, just like any other vector. Now the only difference is that a unit vector by definition has a magnitude of 1, and because the ground frame and the local horizon frame are parallel at all times, that means that their direction is actually the same as well. That means that the unit vectors making up the ground frame and the unit vectors making up the local horizon frame are mathematically equivalent. They have the same magnitude and the same direction. So now we can actually use that to define our position vector EO, and that is x of I minus h of k with a minus sign in front of h because positive k points down. So if you have a positive altitude, it's going to be negative. And you see that all of that is equal to x of IH and h of kh, which is the expression expressed in the local horizon frame, and that is equal to what you have on the left. In terms of the velocity vector, we know that it is defined in the wind frame, and all you need to do to express it in the local horizon frame is to use what we had derived in the previous lecture and multiply that expression by v the velocity, which is what you see at the top. Now finally, the last component we want to be able to exploit is that the derivative of the position vector is equal to the velocity vector, and this is what you see at the bottom. So what you need to do here is to take the derivative of x of IH minus h of kh and equate that to the expression for the velocity that we have just found. Then, finally, what you need to do is to separate the I component and the k component, and what you get are the horizontal and vertical velocity expressions. So this is what we're going to use to track the motion of the aircraft in the vertical plane. Next, what I want to talk about are the sum of the forces. At this point in time in the book, the equations of motion are going to be expressed in the wind frame, and that means that the aerodynamic forces, and that is drag and lift, are already defined in the wind frame and are not going to require any adjustments. Now we're left with thrust and weight, which will both require some adjustments. Usually, when the equations of motion are being defined, the forces are summed along the x-axis, y-axis, and z-axis separately, and then set equal to mass times acceleration along the x-axis, y-axis, and z-axis respectively. Here, they're all combined, so the forces are actually equal to lift plus drag plus thrust plus weight. So in order to express the weight vector in the wind frame, all you need to do is to use the transformation matrix that we had derived last time and multiply that by the weight vector expressed in the local horizon frame, and you will get your new components of the same vector, but this time expressed in the wind frame. Finally, to express your thrust vector in the wind frame, you need to project T onto IW and KW to get your new components. So the projection of T onto IW is going to be T cosine of epsilon, and because the direction of that projection is in the same direction as positive IW, it is going to be a positive contribution. Finally, the projection of T onto KW is going to be T sine of epsilon, and because the direction of the projection is in the opposite direction to positive KW, it is going to be a negative contribution. So this is what you see here. The thrust is expressed in the wind frame, drag and lift are expressed in the wind frame as well, with minus drag in front of IW because drag acts along negative IW, and the same thing for lift because positive KW points down. Finally, your weight vector expressed in the wind frame is what we just found earlier. So all you need to do now is to combine everything and separate your I and K components. Alright, this is it for today. Thank you very much. See you next time.